Bismillahirrahmanirrahim. Assalamu alaikum viewers, welcome to my channel, and in today's video, as you can see the topic, we are going to discuss the first order linear differential equations, how to solve them. So what exactly the general form of linear differential equation of order 1? You see all those ODE that can be written or they are already written in this form. In this form, and this is said to be linear differential equation form, where you can see that y, which is basically the function of x, so this is the dependent variable and x is the independent variable. So over here, when you will find two functions p of x and q of x over here written in this way, then this pattern or this kind of ODE is called a linear differential ODE. Okay, so this is it. So what exactly the way of handling or solving first order linear ODE and how to get its required solution? We are going to understand here the methodology, and I must say that the process of solving linear differential equation, in order to understand the process, we have to understand first the methodology of how to solve the exact first order ODE. So those who haven't watched my videos related to the exact differential equations of first order, I humbly suggest them to watch those videos first and then come and have a look on this video, linear differential equations. Okay, so we can further write this equation in this form if we take the LCM at the left hand side. Then this x will move over here. Okay, so I'm going to combine my dx terms together. I better enclose them in square bracket instead of curly. So it's this. Okay, so you can see that I have just reduced this linear differential equation of, in this form that looks like exact differential equation that I have already discussed quite exhaustively in my videos related to this topic. So I need to know, is it really exact in form or not? So I'm going to take the partial derivative of this m with respect to y and partial derivative of n with respect to x. If they are equal, then we say that this equation, I just call this equation 1 and this as equation number 2. Okay, so I will say that this equation number 2 is said to be exact, but let's see that is it really giving me equal answer. So when I will take the partial derivative of this m, this is my m with respect to y, I'm going to get just p of x left here. Okay, and in the same way I'm going to take my n is 1 here, as you can see. When we compare this equation with this 2 equation, we can see that n is 1. So when I take the partial derivative of n with respect to x, my n is 1, so it is going to give me nothing but 0. Okay, so you can see that partial derivative of m with respect to y and partial derivative of n with respect to x, they are not equal. Okay, so this equation is not exact, it is non-exact. Okay, so it will be exact once when p of x will be 0. So we need to introduce here an integrating factor. As we have discussed already, there are near about 4 rules of obtaining integrating factors of a non-exact differential equation in order to turn it exact, and then we just solve them out. So we have discussed all those 4 rules in the previous videos. You can just have a look. You can see the links in the description box. So it is really strongly recommended that you should watch those videos. If your concepts are not that much clear in exact differential equations, then you should watch them, and after that you come over here. So we have to introduce an integrating factor. So once when we obtain the integrating factor of this equation, then and we represent that integrating factor with mu x. So once integrating factor mu x will be obtained, we are going to multiply this integrating factor with this equation number 2 entirely. Okay. With this equation number 2 whole. Okay, that's how it looks like. And once now when you take the partial derivative of this m and this n according to according to this strategy, then it will be equal then. That's what I exactly mean. So definitely it will turn exact because we are using integrating factor, and integrating factor is indeed a tool of converting non-exact differential equation into exact form. So that's what exactly it means. So you see here the partial derivative of this whole thing is m, right? So the partial derivative of this m with respect to y will be equal to partial derivative of x, partial derivative of this, mu of x with respect to x. Mu of x is n here, basically. So once after the application of integrating factor, this is definitely gonna happen. Okay, so that's why we have just written it directly. Okay, so that's what exactly it is. So once when you differentiate this expression with respect to y, you're going to get just this thing left. This is actually the background how we are going to understand how to solve the linear equation. So that's why we are just trying to do it. That's it. Okay, so now we are going to we can simply solve this thing in this way as well. Instead of writing mu of x in short, we can write in this way too. And instead of using partial derivatives, we are going to write this thing. Okay, now we can apply the strategy of we can apply the method of separating variables. The video related to that thing as well is also mentioned in the description box. You can watch it if you want to. So we are going to use this thing here. So you're going to swap the variables according to the differential operators. So now you're going to integrate both sides. So once when you integrate both sides, then this is going to be your ln or log of mu. Okay, it's going to be your log of mu and I'm just copying this thing as it is. Okay, and once in order to remove this log thing, we are going to take the anti-log, so we are going to take the exponential, the Euler number exponential here. So once when you take the exponential, it will look something like this. Okay, alright, so you can also express this exponential representation in this way too. Okay, you can also express like this. Alright, so you see this is an anti-log thing, so it is going to cancel out the effect of the log, and just mu is going to be left here. So mu is basically your integrating factor, as we have discussed already. This is your mu. So mu we have just obtained through this way. Okay, so in order to once when we obtain this integrating factor, we are going to multiply this integrating factor with our equation number 1. Okay, so actually the integrating factor of the linear differential equation has been obtained, and this has been so understood by the help of exact differential equation pattern. Okay, or more precisely, we say that it is so obtained or so understood with the help of non-exact differential equation. So that's why we just converted this form into this first, and then we applied this entire method. We obtained the integrating factor that is going to be used for your linear differential equation. Okay, to how to solve it. So once when we obtain this integrating factor, we are now going to multiply this integrating factor with our linear differential equation, and we are going to get something like this. Okay, that's how it looks like. Alright, so as our integrating factor is this, so we are going to multiply this with both these terms one by one. Alright, so if we just try to focus over here, from here to here, you can see that this is the derivative of u into v concept. It is following the concept of a derivative of product of two functions. So we can express it like this. Okay, so once when you apply the derivative on the product of two functions, you're getting this thing. So this is the expanded form of this thing. So I just enclose it by using the formula of the derivative of product of two functions. Okay, so, and this is going to be copied as it is like this. And once when you integrate both sides, then okay, so this differential operator is going to cancel out the effect of your integral, and thus just the function is going to be left. And you solve this thing, you're going to get definitely some answer, and that answer is going to be written over here plus some constant. So that's the thing is going to be, that's how the linear ODE is going to be solved. Alright, so this is basically the theory of how you obtain the integrating factor. That's what exactly we were discussing up till now. So now we move ahead to the example. Alright. Okay, so this is a beautiful example. Let's see, can we write this differential equation in the form of a linear ODE? So if we divide this entire equation with x minus 1 whole cube, so we are going to get something like this. Sorry, it's plus. So I'm dividing my entire equation with the term so attached with dy by dx. So you can see we can cancel up these two terms because they are like in nature. So I'm having simply x minus 1 here left, and I can just write it like this into y equals to x plus 1 upon x minus 1 whole cube. This is it. So you can see that it is for following the general pattern of your linear first order ODE. Okay, so you can see that this thing is my p of x and this is my q of x. And as we have studied a moment ago, that the integrating factor for the linear first order ODE is this. Sorry, it's x. Okay, that's what we have studied. So if we just apply here this tactic, then we are going to get okay, so this is going to give me ln of x. It's going to give me ln of x minus 1, yeah, and I can use the basic characteristic of my log. I can write this thing in this way, okay, and then exponential is going to cancel out the logarithmic effect, and just x minus 1 power 4 is left, and this is my integrating factor. So I am now going to multiply my integrating factor with this entire equation, the linear equation. I just call it equation number 1. Alright, so I'm going to multiply my integrating factor with this whole. Okay, that's how it looks like after multiplication. Now we are going to multiply term by term. When I multiply this thing with this, I'm going to get 4x minus 1 power 3y. Okay, and over here, once when x minus 1 power 4 and x minus 1 power 3 is going to be multiplied, so I'm going to have this thing left, and this is actually x squared minus 1. Okay, so this thing is equals to this here. Alright, so now, as we have just discussed already, we are going to use the formula of the derivative of product of two functions. So I can write this expanded form in this enclosed form. Okay, again I should use square bracket instead of big bracket. Alright, and this is going to be x squared minus 1. Now I will integrate both sides. So once when I integrate both sides with respect to x, of course, okay, so I'm having yx minus 1 power 4 left here, because this derivative is going to cancel out the integrating effect, and just the integrand, or just this function is going to be left. And over here we apply regular integration. It is going to be x cubed upon 3 minus x plus some constant. Alright, so in this way we come to know that the value of y will be, this thing can be divided over here, and you will simply get an equation keeping y the subject, or you can leave this thing as it is as well. It's your choice. So this is that's how you solve a linear ODE with the help of the integrating factor that we have understood in the light of our non-exact differential equation. Okay, so that's all for today. And if you find this video helpful, please subscribe my channel, hit on the like, and share these videos. And don't forget to put your comment in the box below. Take good care of yourself. I'll see you in future with more examples on linear differential equations. Take good care of yourself. Once again, Allah Hafiz.